In this video, we're going to be talking about interpreting and communicating the results of statistical analysis. So what is the most common way to summarize multivariate data? The answer is a regression model. It's important when reporting the results of a data analysis involving bivariate numerical data to include graphical displays as well as numerical summaries, including a scatter plot, providing a description of what the plot reveals, about the relationships between the two variables, numerical summary measures such as correlation coefficient or the equation of the least squares line. All of those things can be interpreted. So here are a few things to look for in other people's data. What about the variables? What two variables are being studied? Are they both numerical? Is it a distinction has been made between a dependent variable and an independent variable? Is there a scatter plot? Does the article include a scatter plot of the data? If so, does there appear to be a relationship between the two variables? Can the relationship be described as linear, or is some type of nonlinear relationship a more appropriate description? Strength. Does the relationship between the two variables appear to be weak or strong? Is the value of the correlation coefficient reported? Measures of fit. If the least squares line is used to measure the relationship between the dependent and independent variables, is any measure of goodness of fit reported, such as the R squared or your S sub E, so your standard deviation? How are these values interpreted? And what do they imply about the usefulness of the least squares line? Is it just a line? And if there's a correlation coefficient, how is it interpreted? You need to be cautious of interpretations that claim a causal relationship. So again, when we think about what are these fools trying to say to us, we want to think, what about Bob? So our variables. Is there a scatter plot? Like, bro, do you even lift? Think about the strength. Is it just a line? And correlation, interpretation, gyration. Which again means that we want to make sure that our correlation coefficient is being interpreted properly. And now for the warnings. If you learn one thing in this class, correlation does not imply causation. A common media blunder is to infer that a cause and effect relationship between two variables simply because there's a strong correlation between them. Don't fall for this trap. A strong correlation implies only that the two variables tend to vary together in a predictable way. But there are many possible explanations for why this is occurring besides one variable causing a change in the other. Remember our example about drinking hot chocolate and crime rate going down. You're not just going to give everybody a bunch of hot chocolate and the crime rate's going to go down. Remember that the reason why there's a correlation there, or it appears that there is, or a causation, is because the cold weather drives both of those themes. Second, near zero correlation coefficients. A correlation coefficient near zero does not necessarily imply that there is no relationship between two variables. Before such an interpretation can be given, it's important to make sure you examine a scatter plot of the data carefully. Although it might be true that the variables are unrelated, there may in fact be a strong but non-linear relationship. Third warning I've got. Who's wearing the hat? The least squares line for predicting y from x is not the same line as the least squares line for predicting y from x from y. The least squares line is by definition the line that has the smallest possible sum of squared deviations of points from the line in the y direction. The line that minimizes the sum of squared deviations in the y direction isn't generally the same as the line that minimizes the sum of the squared deviations in the x direction. So are you looking at the x hat or at the y-hat. Let's look at some more warnings. Extrapolation is your friend. Beware of extrapolation. It is dangerous to assume that a linear model fit to data is valid over a wider range of x values. Using the least squares line to make predictions out of the range of x values in the data set often leads to poor predictions. What's the intercept mean? Be careful in interpreting the value of the slope and the intercept in the least squares line. In particular, there are lots of instances interpreting the intercept as the value of y that would be predicted when x equals 0 is equivalent to extrapolating way beyond the range of the x values in the data set. And this should be avoided unless x equals 0 is within the actual range of the data. Next, make sure you try your model on. You want to make sure it looks good. Remember that the least squares line may be the best line in that it has smaller sum of square deviations than any other line. But that doesn't necessarily mean that a line will produce good predictions. Be cautious of predictions based on the least squares line without any information about the adequacy of the linear model, such as your standard deviation and your r squared. 3 more warnings. Which is better, s or r squared? It's not enough to look at just r squared or s when assessing a linear model. These two measures address different aspects of the fit of a line. In general, we would like to have a small value for s, which indicates that deviations from the line tend to be small, and a large value for r squared, which indicates that the linear relationship explains a large portion of the variability in the y values. It is possible to have a small s combined with a small r squared, or a large r squared combined with a large s. Remember to consider both values. Next warning. So there's a song by Ralph Tresvant called Sensitivity. See, the value of the correlation coefficient, as well as the values for the intercept and the slope of the least squares line, can be sensitive to influential observations in the data set, particularly in the sample size, if the sample size is small. Now, because potentially influential observations are those whose x values are far away from most of the x values in the data set, it's important to look for such observations when examining the scatter plot. Another good reason for always starting with a plot of the data. And our final warning, lines are for linear data. If the relationship between two variables is nonlinear, it is preferable to model the relationship using a nonlinear model rather than fitting a line to the data. A plot of the residuals from a linear fit is particularly useful in determining whether a nonlinear model would be a more appropriate choice. So by heeding these 9 warnings, and by also making sure you know what to look for in published data or data from other people, this should help you have a better chance at coming up with interpreting and communicating the results of statistical analysis better.